Alright, good people, this is section 2.6, Formulas and Problem Solving. Now with our newfound knowledge of how to solve quadratic equations, we're going to return back to yet another section. Yes, it was section 2.3 and 2.6 both have the same name and the same objective. But now that we know more, we can do more. Like this. Now that we know how to solve quadratic equations, we can solve something like this formula for r. So, the first thing I'm going to do is clear the fractions. So we get 3v equals pi r squared h. I'm going to divide both sides by pi. I'm going to divide both sides by h. And we get 3v over pi h is equal to r squared. And then we're going to take the square root of both sides. And we get r equals the square root of 3v over pi h. Now technically there is a plus or minus here, but because it's geometric, we are only going to talk about positive radii and positive volumes and positive heights. Although when you get to calculus in a couple of years, then even things like negative distances and negative areas are completely normal and possible. Oh, look at that cone. Isn't that beautiful? That was for the volume of the cone. Here, we can solve for t now if we want to. This is an equation for position of something that's being dropped, an object that's being falling to the ground. And it's telling you what's the distance. We'll describe it later down here, what the t and the v0 and the s stand for. But for right now, let's just solve. It's a quadratic equation because the variable is t. So because the variable is t, we've got a t squared term and a t term, and then a constant term over here. Let's make it all equal to 0. 16t squared plus v0t minus s. And because this is a quadratic equation, we can just plug a equals 16, and b equals v0, and c equals negative s into the quadratic formula. And what we get is this. You get t is equal to the negative b plus or minus the square root of b squared minus 4ac all over 2a. And of course you can simplify this a bit further. You can multiply the 4 and the 16, cancel out the negative and minus, and then multiply 2 times 16. But for right now, that's all I really want to write. I'm just going to leave this as it is. You can simplify it later, but I don't have space, and I don't really feel like it right now. Ha! So, compound interest, Pythagorean theorem, and objects dropped or thrown downward. These are three new scenarios that we can continue to develop a bit more completely now that we are mastering our quadratic equations. So, compound interest, a equals p times 1 plus it. A, remember, is the final amount of money that you've got in the bank. P is the principal amount, the starting amount. I is the interest rate, usually expressed as a decimal when you're plugging it into the formula. And then T is time in years. So, of course, the strategy is going to be listing the knowns and unknowns, as usual. So, an investment of 2560, that's known. 2560. That sounds like a starting amount. Is made at an interest rate I. I don't think we know the I. It's just telling us I. Compounded annually. Okay, so that's the formula we're using. In 2 years, T equals 2 years. It grows to 2890. What is the interest rate? Yeah, so we don't know the I, but we can figure out everything else. Using the formula A equals P1 plus I to the T, we fill in everything we know, and that is this. 2890 equals 2560 times 1 plus I squared. Oh, this looks like a quadratic equation. Let's undo the multiplication first by dividing both sides by 2560. Like this. Then we get, using a calculator, approximately 1.13 is equal to 1 plus I squared. Taking the square root of both sides, again using a calculator, we get 1.0625 equals 1 plus I. I'm going to ignore the plus or minus because we know we can only have a positive interest rate. Then when you subtract 1 from both sides, you get your answer. I is equal to 0.0625 or 6.25%. Next, a 13-foot ladder leans against a wall. The bottom of the ladder is 5 feet from the wall. The bottom is then pulled out 4 feet further. How much does the top end move down the wall? Wow, let's draw a picture. Let's draw 2 pictures, a before picture and an after picture. Before, the ladder starts out with 13 feet long, and the other unknown that we have is that it's the bottom of the ladder starts out 5 feet from the wall. The bottom is then pulled out 4 feet farther, so 5 plus 4 is 9. This bottom part is 9 feet, and then the hypotenuse of this triangle is still 13 feet. Question is, how much does the top end move down the wall? Well, I guess my unknown is the amount of decrease, the decrease in the height. So I'm going to need to find the before height and the after height. I'll call this, I'll call this A and I'll call this B. And what I really want to know is what is A minus B. So we have 5 squared plus A squared is equal to 13 squared. And we also know that 9 squared plus b squared is equal to 13 squared. So just talking through the math, 5 squared is 25, and you subtract that from 13 squared, which is 169, you get a total of 144. Taking the square root, you get 12. This is the kind of problem that many of you have seen before, and you know that because we're dealing with actual lengths of ladders that can't be negative, we're going to ignore the negative solution, so just A equals positive 12. Then 9 squared is 81, 13 squared is 169. When you subtract the 2, you get 88. B squared equals 88. And when you take the square root of both sides, you get plus or minus approximately 9.38, but we're going to ignore the negative solution, so just B is equal to 9.38. So A minus B, in the end, is going to be this. A minus B is, using a calculator, you get 2.62 approximately. 2.62 what? Feet. That's how far the ladder decreased in height. And so one thing I want to do before we move on is go over this formula that I referenced before. As objects drop, it's the equation that governs the motion about objects that are falling. And there are 3 different variables here. T is time, V0 is the initial velocity, the starting velocity, the velocity that, not at the end, not at the middle, but at the very beginning of this whole thing, how fast the object is traveling. And if you're dropping something, then if you're really thinking about it, then this is equal to 0 if you drop it. So if you throw something downward, then it has a positive initial velocity. But if you're just letting something go, at the instant that you let it go, it's just hovering there in air. And V0 is equal to 0. The velocity is 0 if you're just dropping something. Then it starts to gradually pick up speed until it eventually hits at the bottom. Here's your audio check. Did you know that Pythagoras, whose theorem that we used at the ladder problem, was born in 570 BC, died at 495 BC, and legend and obfuscation cloud his work. So it's uncertain whether he truly contributed to mathematics or natural philosophy or what, because some of his stuff might have been done by his followers. Anyway, Pythagoras, crazy guy, brilliant, influenced lots of people, and we still use his formula today.
Alright, good people, so before we do the next three examples, which are related to each other, I want to give you another equation, and it's a very similar equation to a previous one that you've seen on the other page. S equals 4.9 t squared plus v0 t. Now the only difference between that one and the previous one is a 4.9. That's because this one is an equation that is used whenever you're talking about meters. The units on the 4.9 are related to meters, and the units on the other one are related to feet. So anytime you're doing something related to meters, like in this one, you can see it's one of the knowns is 92 meters. Then you use this equation with the 4.9. And I'll tell you why in class if you like. The knowns are, of course, S is going to be equal to 92 meters, and the fact that the object is being dropped from the top of the Statue of Liberty. So that means the v0 is going to be equal to 0. The initial velocity is 0. At that instant, when you drop it and you let go, if you could take a picture, that freeze frame would show that the object is not going anywhere. It has an initial velocity of 0, and then eventually it starts to pick up speed. What you really want to know is how long does it take for the object to reach the ground. So therefore, the t is we don't know what the t is, we have to try and find that out. So the equation we're going to use, because of the 92 meters, is going to be S equals 4.9 t squared plus v0 times t. Substituting in the value for S is 92 meters, and the value for v0 is going to be 0. That crosses out that one term, and then with our newfound quadratic skills, we can divide both sides by 4.9 and get 92 over 4.9. Taking the square root of both sides, you're going to get, with a calculator, about 4.3 seconds. Now, of course, mathematically you get plus or minus 4.3 seconds, but in the experiment we can't get a negative answer, so we just give the positive version. An object is thrown downward from the statue at an initial velocity of 40 meters per second. I don't know why someone's going to propel something down off the Statue of Liberty at 40 meters per second. It's like, I don't know, putting a hot dog in a hot dog cannon and pointing it downward really fast. 40 meters per second, if you think about it, is super fast already. Anyway, that's the initial velocity. You're pointing that hot dog cannon downward at the crowd, and let's see, it takes 92 meters to get down there. That's the distance. We still want to know what the time is. We're going to use the same equation. Because we're working in meters, we use the 4.9 version. S equals 4.9 t squared plus the initial velocity times t. And then we're going to fill in the knowns. 92 meters, 4.9 t squared plus 40t. Now, if you want to solve this, it's a quadratic equation. If you want to use the formula, then we have to set it all equal to 0. 0 equals 4.9 t squared plus 40t minus 92. And of course the a, b, and c values, if we use the quadratic formula, are a equals 4.9, b equals 40, and c equals negative 92. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. I think it's a good practice to make sure you copy down the formulas every time you use them. That way you practice writing them out. Negative 40 plus or minus the square root of 40 squared minus 4 times 4.9 times the c value, which is negative 92, all over 2a. Now, you could put this immediately into a calculator, Depending on your calculator, it might be easy and it might be beneficial enough to calculate the discriminant first. But in any case, you get 1.9 seconds if you're using the plus of the plus or minus. If you use the negative 40 minus the square root, then you'll get another answer, which mathematically will make sense, but it'll be negative, and so therefore we just want to discount it. How far will an object fall in 1 second if it is thrown downward from the statue at an initial velocity of 40 meters per second? Okay, so the known here is t equals 1 second, v0 equals 40 meters per second. And what do we want to find out? We want to figure out how far the object will fall. It's an unknown distance. Might not be the full 92 meters of the Statue of Liberty. In fact, we're pretty sure it won't be the full 92 meters because we just calculated in 5b, the last example, that it'll take 1.9 seconds. So where is it going to be after 1 second? The formula we need is s equals 4.9 t squared plus v0t. Plugging in what we know, which is t equals 1 and v0 equals 40. You get all that. And then when you do the order of operations, you get 44.9 meters. And that's the answer. Alright, good people. There it is. I'd like you to begin assignment 2F. That means copy the problem list and start the first problem in your composition books. And I'll see you in class.